Welcome to 5.3. We're going to be graphing in factored form. This is the first time that we're going to graph polynomials higher than like x squared, which we've seen in the past. We did do a little graphing. We talked about some of the characteristics, and we're going to see that again today. So graphing in factored form is nice because we're always going to be able to see the roots. We're going to be able to see the x-intercepts. So it's pretty easy to start out with graphing, just like we saw back when we were graphing parabolas. So this is our equation. It's f of x equals a times x minus the root for all of these. Remember that when we see a minus root, we're always thinking the opposite sign. So in the parentheses, if we see like x plus 4, that's actually going to be a negative 4 as the coordinate. And then we're going to be looking at that end behavior again. We're always going to want to think about like which direction are the tails going to go? Does our graph match up with the characteristics that we've learned about so far? And then also thinking about those turning points. We talked about the turning points because the degree is always 1 greater than the turning points, or it has to be at least 1 greater. So what we're going to do first is we're going to graph with our graphing calculator and then describe the roots here. So I'm going to be using Desmos again. We have a cubic equation, so we're expecting 3 roots. How many total roots does the polynomial have? We know it has to have 3. So let's go ahead and graph this. Always want to double check as you're going through. Okay, so now I'm going to zoom in on this one now that I have that graphed. And this one looks to be, yeah, it doesn't look like we're crossing at any other points. We are just going through one point here, and it looks like it's exactly at 1, 0. So that means that we have one real solution, because real solutions will always cross through the x-axis. Because we don't have any other points that are going through it, we can assume that the other 2 are imaginary. And remember, imaginary roots always come in pairs. So if you know that there's one imaginary root, you know there's actually 2 for that same imaginary root. Okay, so we would have 1 real, 2 imaginary. And like we learned in 5.1, we can solve for those. We could use that first root that we saw, break it down, and then be able to solve. So complex imaginary roots always come in pairs. I kind of mentioned this. The reason is because imaginary roots come from the square root. And when we take the square root, we always end up with that plus or minus situation. So that's why there's always 2 of them. So it's plus or minus 3i in this case. So now we want to answer the question, if you have a 5th degree polynomial and you're given one imaginary solution, what is the max number of real roots? Okay, so the fact that we have 5 solutions and 1 is imaginary, if there's at least 1 that's imaginary, that tells us that there's automatically 2. You have to have an even number because they come in pairs. So then we would have 2 imaginary, and you don't have to write this part, it's just asking for the maximum number of real, which in this case would be 3 real would be the max. And I probably should have put 3 real roots. Okay, now we're going to sketch a graph of a polynomial function that has 5 roots, including imaginary roots, x equals 3i and x equals 2 minus 5i. So what they're trying to show us here is the fact that if we have a 3i, that means we also have a negative 3i. Same thing with this one. If we have 2 minus 5i, we also have 2 plus 5i. They come in pairs. So of the 5 roots, that guarantees that actually 4 of them are imaginary and only 1 of them would be real. So we want to graph with the following end behavior. It's x approaches infinity, which if you remember that means as x goes to the right, f of x goes down since it's negative infinity. So as we go to the right, we're going to end up going down. This one states as x goes to the left, f of x goes up. So we need some kind of graph that has this end behavior here, and it can only cross 1 time since we only have 1 imaginary, or 1 real root, excuse me, the rest are imaginary. So you could do something like this, and if you wanted, you could add in a few more turning points. You don't have to. as long as that end behavior matches and you only cross one time. So would the polynomial have a positive or negative leading coefficient? In this case, since it's going down, that would end up being negative. So then it would be A is negative. I'll write out the word negative. Okay, now we're going to continue on here. It says solve x squared plus 4x minus 5 equal to 0. Are the solutions real or imaginary? And what does that mean in the context of graphing? So here, we could try to factor this one. So are there factors of 5 that have a difference of 4? Yes, it would be positive 5, negative 1. So in this case, since we can factor it, those solutions should be real solutions because we know it would be 1 and negative 5. So those are real. There's no imaginary part. And what does that mean in the context of graphing? We see them. We can see roots on the x-axis. They're visible to us. Okay, so now this is going to lead us into the factored form of graphing where we can actually plot these points to start out. So when we're thinking about the degree, it's a little bit trickier when it's in parentheses, but if you were to think of this as 1 and 1, we are multiplying. We could FOIL this out and write it in like standard form, but since the exponents are 1 and 1, we would multiply those and we'd get x squared. So this is actually going to be a second degree or a quadratic. The end behavior here, if we want to do a little sketch, or we can write it out as x approaches infinity and as x approaches negative infinity, f of x would go, so this is the case where since it's an even degree, we know it has to go the same direction. And since our a value or our leading coefficient here is a positive 1, we can assume that both of them are going to go up. The x-intercepts would be the 2 points, x minus the root, x minus the root. So it would be 2, 0, and 4, 0. They're positive because we think of the opposite. And we can plot those points. 2, 0 is over 2 right here. 4, 0 is right there. Now, the way that we're going to make a table here, this table is going to vary. It's not going to be consistent every time. So it's always going to be an x and y table. What we want to do here is look at the point on the left. Notice 2 is our furthest left point that we see. We always want to go at least 1 to the left of that. So 1 point to the left of 2 is positive 1. Then you want to try to get a point in between the two. So in this case, the number between 2 and 4 that's perfect is 3. And last, we want to go 1 to the right. We want to get a point on the other side of our furthest right point. So 1 point to the right of 4 would be 5. So these are the points that we're going to plug in and solve. Okay, and the way that we're going to plug them in is we're just going to take each of them and plug them into the original equation for both of the x positions. All right, so it would be 1 minus 2 times 1 minus 4, that's negative 1, and negative 3, which ends up being 3. So that's our first point. So 1, 3 is right here. You don't have to plot them at the same time. You can get it all in the table and then plot it. Then we would have 3 minus 2, 3 minus 4, which would be 1 times negative 1, which is negative 1. And that's right down here. And then we can go ahead and do the next one, which is x minus 4. We would plug in 5 for the last set. I'm going to do it over here. So it would be 5 minus 2, 5 minus 4. This would be 3. This would be 1. And we get 3. Which again makes sense because we were expecting a second degree polynomial, which is a parabola. And that's exactly what shape came out of it. This matches our end behavior because both of them are going up if we were to connect these points. So we know that we are probably on the right track. And there you go, your first one graphed with this method. Okay, we're going to move on to the next one here. Now we're on example 2. We want to graph f of x equals 1/5 x minus 3 cubed times x plus 1 squared. So in this case, since this is like 3 sets of parentheses and this is 2 sets of parentheses, you're just going to add the exponents that you see on the outside. So the degree here would actually be 5. And our a value is positive, that's 1/5. So then for our end behavior, we know that as x goes to the right and as x goes to the left, since it's odd, it's going to go 2 different directions, but they're going to match the original since it's positive. So then this one's positive and this one is negative. If you want to draw yourself a little sketch, it would look something like this. That would be the end behavior. Okay, we again have 2 x-intercepts. We have the opposite of -3, which is 3, and this one would be -1. So it would be 3, 0, and -1, 0. So I'm going to plot those here. Here's 3, here's -1. Now we just got to do the same thing for our table. We want to fill in points that work out really nicely. So we always want to pick 1 to the left of our furthest left point. So since -1 is the furthest left, we're going to go to -2. Here it might be a little tougher to decide. You can pick any point that's in between, but try to get as close to the middle as possible. And it looks like 1 is the direct middle for this one. And then a point to the right of 3 would be 4. So that's all you need is those 3 points, because we're just trying to do a sketch of this. You know, we're not going to be as accurate as Desmos. So then we are going to plug those in for the x values, and then we're going to get those out here. So if you want also, I'm going to show you guys kind of a shortcut what you can do here. I'm going to get Calculator Pro out. So we can type in, and hit the fraction button, 1/5, and then in parentheses I'm going to do -2 is my first x value, and then it's -3 to the 3rd power, because these can kind of get big, so sometimes it's nice to just use a calculator. And then it would be x plus 1, so -2 plus 1 squared. Just double check, make sure you have that typed right, and then you can type this in here. So we get -25, which is a big number, but it's fine. We'll make that work. We got -25, and then we're going to just copy and paste this. We're going to save ourselves some time, and then we're just going to change out the x values. So instead of -2, I'm going to replace that with 1. I'll go over here, delete, delete, replace that with 1. And now I get -32/5, which if you want that answer, so if you want this as, like we can enter that and then just hit math. You want the decimal, it's 6.4. 6.4. Okay, now I'm going to copy this one more time and just hit enter if you want. And now the last one I'm going to do is I'm going to change this to 4. And we get exactly 5. So now that I have those, I'm going to go ahead and graph with this. So -2, -25 would be somewhere way down here. You obviously don't have to go all the way down to 25. Just show that it's going to be beneath the graph. Over 1, 6.4 is 1, 2, 3, 4, 5, 6, somewhere about right there. And then 4, 5 is over 4, up 1, 2, 3, 4, 5 right here. So what happens, and what's kind of weird about this graph, is we're coming from the bottom. It's going to go all the way up till it reaches about there, and then it's going to dip back down, and then it's going to go back up. Okay, and that does match the same end behavior we were talking about. Our left tail is going down, the right tail is going up. It only has 2 turning points, but that's fine. It's a 5th degree, so we know that we have to have, we could have up to 4 turning points in this case. All right, let's go ahead and try our, I'm going to do one here. So the degree on this one, these would all, if there's no exponent, you can assume there's a 1. So it's 1, 1, and 2, which adds up to make 4. So then our a value is negative this time, -1/4. So the end behavior is going to be x to infinity, x to -infinity. F of x is going to go the same direction, and since it's negative, they're both going to go down. Okay, so we're going to have some kind of even shape where they're both going down. Might not be a parabola, it might look similar to one, but. And then our x-intercepts, this time we have 3. We have -4, 3, and -1. -4, 3, -4, 0, 3, 0, and -1, 0. Okay, so 1, 2, 3, 4 right here, 3, 0 right there, and -1, 0 right here. Okay, now our table this time, we actually have to bump it up because we have more points where we can put in between. We still want to go to the furthest left point, which is -4, and we're going to go one to the left of that, which is -5. Then we have 2 points to choose from here. Between -4 and -1, there's -2 and -3. Doesn't matter which one you pick. I'm just going to go with -2. Next set, we have point in between -1 and 3. The perfect number for that is +2 because we see that that's directly in the middle. And then we just need 1 to the right of 3, which would be 4. So this time we're going to have 4 points. The more x-intercepts you have, the more points you need to have in between them. So now I'm going to split screen with my calculator again. This is just going to save you some time, especially when you're working with fractions and stuff like that. So now I'm going to clear this out. I'm actually going to type this one as -1 divided by 4 rather than hit the fraction button, because this is going to automatically give me the decimal instead of the fraction version of the answer. So the first point that I'm plugging in here is -5 instead of the x. So -5 plus 4, and then it would be -5 minus 3, and the last one is -5 plus 1. And then I want to square that. Now just double check, make sure you typed it in correctly, because we don't want to mess that part up. And we're going to hit enter, and we get -32. Sometimes the numbers are going to be kind of big, and that's okay. Okay, now again, save yourself some time, copy and paste this down here, and then just change out the x value. So delete, delete, don't hit clear. Now I'm going to do -2. Delete, delete, I'm going to do all of those as -2. And then we're going to hit enter, and we get 2.5. See how it gave me the decimal this time? I like that. All right, and you'll get kind of quick at this part. Actually, I can just delete the negative signs because it's +2 now. Enter, we get 13.5. And then I'm going to do one more here, which is 4, 4, 4, and I get -50. Okay, so now I'm going to finish this problem here. -5, -32, that'd be somewhere way down at the bottom, so I'm just going to show that it goes off. -2, 2.5 is about right here. 2, 13.5 would be somewhere up above, so this one does kind of stretch off. And then 4, -50 would be way down here as well. So now when you connect your points, always start on the left side, go up, goes down, try that again, goes up, and then once we hit this point, it actually is going to bounce, and then it's going to go way up here to this one. Go all the way down, connect to that last point. And this does match the end behavior. Okay, for the sake of the length of this video, I'm going to stop it here. Thanks for watching.